A wall of ice the size of Florida is being held in place by a single point on the ocean floor. And that point is coming loose right now. Scientists who study this glacier are no longer talking about decades as the relevant time frame for the next critical event. Some of them are saying the first major structural failure could happen this year. What follows from that failure, the acceleration it triggers in one of the most dangerous bodies of ice on the planet, would unfold over the years and decades afterward. But the starting signal may be closer than almost anyone outside the scientific community realizes. Let me walk you through exactly what this glacier is, why one weak point on the seafloor matters so much, what the newest research says about how close that point is to failing, and what happens to ocean levels globally when it does. None of this requires exaggeration. The honest version of this story is alarming enough on its own. Start with the glacier itself, because without appreciating its scale, nothing else in this story lands the way it should. Thwaites Glacier sits in West Antarctica. Researchers gave it a nickname years ago that tells you precisely how seriously the scientific community takes it. They call it the Doomsday Glacier. It is the widest glacier on the entire planet, stretching approximately 120 kilometers across its front, roughly the same width as the state of Florida, or the entirety of Great Britain from coast to coast. It is also close to 2 kilometers thick. If you tried to walk from the glacier's surface to its base, you would cover more than a mile of solid ice before reaching the rock beneath. This is not a remote curiosity. This is a body of ice roughly the size of an entire American state, sitting at the bottom of the world, and its structural integrity is compromising in ways that researchers have been watching with increasing alarm for years. Now, here is the specific mechanism that makes this particular moment more urgent than the general long-term concern about Antarctic ice. In front of the main glacier body, there is a floating slab of ice called the Thwaites Eastern Ice Shelf. This shelf is approximately 350 meters thick and extends outward from the main glacier over the open ocean. The function it performs is critical, and the analogy that makes it clearest is this. Think of it as a cork in a bottle, or more precisely, as a support beam leaning against a wall that is trying to fall forward. The floating shelf presses back against the glacier behind it. That pressure is what slows down how fast the glacier can slide into the sea. Remove the cork, and whatever was being held back now has nothing preventing its forward movement. Here is where the story becomes genuinely startling. That entire floating shelf is largely held in place by one single spot on the seafloor. There is a place where the ocean bottom rises into a ridge. The underside of the ice catches against that ridge the way a fingernail catches on the edge of a table. One single point of contact between ice and seafloor is doing an enormous share of the work required to restrain a shelf that is in turn bracing a glacier the size of Florida. A 350-meter slab of floating ice is holding back a body of ice more than 5 times its own thickness. When you sit with that fact, the alarming part is not simply that the anchor point might fail. The alarming part is how much has been resting on so little for so long. Structures carrying disproportionate loads rarely fail slowly and gently. They tend to hold and hold and hold right up until the moment they let go all at once. So how do scientists know this anchor point is actually close to failing, rather than simply estimating based on general concern? The answer comes from a detailed study published in 2025, and it is built on measurement rather than modeling assumptions. Researchers gathered approximately 20 years of data covering the period from 2002 to 2022. They combined satellite imagery, measurements of how fast ice is flowing, and GPS instruments physically installed into the ice itself. They tracked how cracks inside a specific weak zone of the shelf behaved across 2 full decades, watching those cracks spread and grow the same way you might track a fracture slowly working through a car windshield across multiple seasons. This is not a single photograph of something that looks concerning. It is a 20-year time lapse of a structure coming apart one season at a time. The weak zone being tracked has a technical name, the shear zone. A shear zone is the area where the floating shelf grinds against slower moving ice and against rock along its edges. That constant grinding concentrates enormous stress into exactly the wrong location. A crack forming in the flat middle of an ice sheet can sometimes stop spreading on its own. But a crack running through the seam that connects the shelf to its one anchor point is a categorically different kind of danger, because it is working directly against the single connection holding the entire structure in place. The 2025 study found that these fractures have been growing steadily year after year, and that growth has been slowly weakening the shelf's grip on its pinning point. Every additional season of cracking loosened the hold slightly more. By the time of the most recent measurements, both the surface and the underside of the shelf are described as heavily fractured, laced with cracks running in multiple directions, and visibly separating from the glacier behind it. The conclusion the researchers reached is direct. They expect the shelf to break apart within roughly the next 5 years. Some scientists studying the same data believe the window is shorter than that, possibly as soon as this year or next. Robert Larder, a marine geophysicist with the British Antarctic Survey who helps coordinate international research on this specific glacier, has said plainly that the shelf is very likely to break up in the near term. This is not a fringe position. This is the considered judgment of researchers whose entire professional focus is watching this particular patch of ice, and their confidence has been increasing rather than decreasing as more data comes in. Now, if you already know something about how ice and sea level interact, an important objection is probably forming in your mind. Let me address it directly, because getting this right matters enormously for understanding what is actually alarming versus what is not. The shelf we are talking about is already floating on the ocean, and a floating object, when it breaks apart or melts, does not raise sea level. It was already displacing its own weight in water before it collapsed. Picture ice cubes melting in a full glass of water. The level in the glass does not rise as the cubes melt because the ice was already pushing aside exactly its own weight in liquid. If the Thwaites Eastern Ice Shelf shatters completely tomorrow, the ocean will not visibly rise the next morning because of that event alone. That is completely true, and any honest account of this story has to say so clearly. Getting that detail wrong is how people either panic about the wrong thing or dismiss the entire warning as inflated nonsense. But here is the critical trap, hiding inside that reassuring fact. The floating shelf was never the danger itself. It was always only the trigger. What sits directly behind the shelf is the actual threat. The main glacier is not floating. It is grounded, resting on land that sits in a basin lying well below sea level. And it holds an amount of ice that is genuinely difficult to visualize. As long as the floating shelf remains in place, pressing back against the glacier, the ice behind it crawls forward relatively slowly. Remove the break from a body of ice roughly the size of a small country, and it begins accelerating toward the ocean. That acceleration, not the cracking of the shelf itself, is what researchers are actually worried about. And the physics that follow make this extremely difficult to simply wait out. Because oceans and massive ice sheets respond to change on timescales of decades to centuries, scientists describe the sea level rise that follows an event like this as largely locked in once it begins, a process that continues playing out for centuries even if the entire planet stopped warming the very next day. The shelf breaking is not the disaster. It is the starting signal for something that does not simply stop on command once it is in motion. To understand why the anchor point is failing in the first place, you have to look at what is happening somewhere no human eye will ever directly see. Deep beneath the ice, the ocean surrounding West Antarctica is not uniform in temperature from surface to floor. There is a layer of relatively warm, salty water sitting well below the cold surface. This warmer water is capable of traveling along the seafloor into places you would not intuitively expect ocean warmth to reach. Because the glacier and its shelf sit inside basins that dip below sea level, this warm water can push far inland, right up against the anchor points and grounding zones holding the ice in place, slowly melting them from below. The real attack on Thwaites is not coming from warm air above. It is coming from warm water below. This is precisely why that single pinning point is coming loose. It is not being eroded by surface weather. It is being eaten away from underneath at the exact spot where the ice grips the seafloor. And this ocean warmth is not some rare or localized event. The world's oceans have been absorbing approximately 90% of the extra heat trapped by greenhouse gases in the atmosphere. Those oceans cover more than 70% of the Earth's surface. All of that absorbed heat goes somewhere, and some of it is making its way to the underside of Antarctica's most vulnerable glacier. You can see this reflected in the global sea level record. A study tracking the overall sea level budget found that ocean warming through thermal expansion, water heating up, and physically taking up more space, accounts for roughly 43% of total sea level rise measured over the past 60 years. But the balance has been shifting. Melting land ice has become the fastest growing contributor to sea level rise since the 1990s. The ocean in this story is simultaneously the weapon doing the damage and the evidence confirming that the damage is happening. For a long time, one of the fundamental limitations in understanding Antarctic glacier behavior was that nobody knew with real precision what the land underneath all that ice actually looked like. That changed significantly in 2025 with the release of BedMap 3, the most detailed map of Antarctica's hidden bedrock ever produced. The scale of the effort behind this map deserves appreciation on its own terms. It combines every usable dataset collected since the 1950s, alongside 84 new airborne surveys conducted by 15 different research organizations, adding roughly 52 million new individual measurement points and approximately 1.9 million line kilometers of radar data. That represents more than 6 decades of information gathered by aircraft, satellites, ships, and in the earliest years, sleds pulled by dogs across the ice, all finally assembled into one coherent picture. This map reveals that Antarctica holds roughly 27 million cubic kilometers of ice, thick enough in some places to reach nearly 4.8 kilometers deep. and it narrows the average distance between any point on the map and an actual physical measurement to about 5.6 kilometers. What you might expect is that sharper measurements would calm the picture down the way better instruments usually shrink uncertainty in most areas of science. Instead, every improvement in mapping and modeling has revealed more basins sitting below sea level and more pathways for instability than anyone previously realized. The clearer the view has become, the more dangerous the underlying setup has actually looked. Antarctica is essentially two different continents hidden under the same ice sheet. Much of East Antarctica sits on solid bedrock rising above sea level, but large sections of West Antarctica sit inside deep basins that plunge well below the ocean surface. Thwaites sits directly inside one of the worst of these basins. This underlying terrain is what allows warm ocean water to creep so far inland underneath the ice in the first place, reaching those anchor points from directions the surface weather never touches. The mechanism that makes this whole process capable of self-perpetuation has a specific scientific name: marine ice sheet instability. It operates through a feedback loop that, once started, has no natural break to slow it down. Here is how the loop works. The grounding line, the exact boundary where the ice lifts off solid ground and begins floating, can retreat backward into progressively deeper water as the ice thins. Thicker ice sitting at that grounding line flows out into the ocean faster than thinner ice does. As the grounding line retreats into deeper basins, the ice sitting there is thicker, which means it flows out faster still, which pulls the grounding line even further back into even deeper water, which means the ice there is thicker still. Each step feeds directly into the next step. The process essentially drives itself once it genuinely gets underway. Models that most closely match how Thwaites has actually behaved in real life already show measurable thinning, reaching roughly 100 kilometers inland along the glacier's main trough. That is precisely the spatial signature you would expect to see if this self-feeding process has already begun. A research study published in early 2026 put specific numbers on where this all leads, and its most significant finding is not a single alarming figure. It is something more analytically unsettling than that. A team of researchers ran two separate, independently built ice sheet models, each calibrated against how Thwaites actually behaved between 2004 and 2017, then projected both models forward to the year 2067. They found that Thwaites could reach annual ice losses of somewhere between approximately 180 and 200 billion tons per year by the 2060s. To put that in context, that approaches the total amount of ice currently being lost by the entire Antarctic ice sheet combined today, coming from just this single glacier. But the genuinely uncomfortable finding is this: the models that most accurately matched how Thwaites actually behaved in the real world over the past 2 decades are also the exact models projecting the largest future losses. In most areas of science, when researchers hope for good news, they hope the scariest possible outcomes correspond to the least accurate models, the ones that fit past observations the worst. In this case, it is the complete opposite. The closer a model gets to correctly matching observed reality, the worse its forecast of the future becomes. That is not something you can dismiss as scaremongering or pessimistic assumption. These high numbers are coming directly from the tools that have proven themselves most accurate against 20 years of hard data. When your most reliable instrument and your most frightening projected outcome turn out to be the same thing, that stops being noise. That is a signal. It is also worth noting that these were two separate models built using different methods, calibrated against the same real-world observations, and they were not disagreeing about direction. They only disagreed on the precise magnitude of future loss, not on whether that loss is coming. That kind of agreement between independent tools built with different approaches is exactly what scientists point to when they want to argue that the ground beneath the conclusion is solid. In fairness, not every researcher agrees on precisely how much the shelf itself matters in its current weakened state. A few earlier studies have argued that the shelf, already heavily fractured as it is, may currently be providing fairly limited support to the glacier behind it, meaning its final breakup might not immediately produce as dramatic a speed increase as some projections assume. Other more recent work suggests whatever remaining support the shelf provides has concentrated into smaller pockets along its edges rather than being evenly distributed. Good science requires being honest about where genuine uncertainty still exists, rather than simply repeating the most alarming version of events. Even with that nuance acknowledged, nearly every researcher working on this glacier agrees on the larger picture. The shelf's disappearance removes one of the last physical barriers in the system, and the surrounding evidence, from the bedrock maps to the fracture studies to the ice flow models, all points in the same direction. A glacier that is speeding up, not slowing down. Let me translate all of this into the number that actually reaches your everyday life. Thwaites Glacier on its own holds enough ice to raise global sea levels by roughly 65 centimeters, a little over 2 feet, if the entire glacier were to melt completely. That alone would be enough to redraw coastlines and flood zones in cities around the world. But because Thwaites functions as a keystone, bracing the other glaciers, draining the wider Amundsen Sea sector of West Antarctica behind it, its collapse could help drag down a much larger stretch of the West Antarctic ice sheet. Pull the keystone from an arch, and the arch does. Not simply lose one stone. The whole structure tends to follow. That larger ice sheet holds enough frozen water to raise global sea levels by approximately 3 meters, close to 10 feet of additional ocean pressing against every shoreline on the planet. 3 meters is not an abstract number on a chart. Coastal researchers estimate that a rise of that magnitude is enough to eventually displace somewhere between 500 million and 1 billion people, depending heavily on how quickly the world constructs defenses capable of holding the ocean back. The places sitting in that path are not unfamiliar. They include low-lying nations like Bangladesh, where tens of millions already live within a few feet of the current high tide line. They include New York, Miami, London, Shanghai, and Tokyo. The specific rate of rise and the timeline over which it occurs determine whether that displacement unfolds as an orderly, expensive, decades-long managed retreat behind newly constructed seawalls, or as something more chaotic and sudden. What we choose to do between now and then determines how much of that outer ceiling we actually end up hitting. The pace of change is already accelerating in ways the measurement record makes clear. Global sea level rose at an average rate of approximately 2 millimeters per year going back to 1960. Between 2005 and 2023, that rate had nearly doubled, climbing to roughly 4 millimeters per year. The trend is not just pointing upward. It is pointing upward at an increasing angle. You may come across claims suggesting this information is being deliberately concealed from the public, or that some kind of targeted technology is intentionally causing this melting. Neither holds up. These research studies are openly published in major peer-reviewed scientific journals and freely available to anyone who wants to read them directly. The reason this story does not dominate front pages every day has nothing to do with suppression. There is no single dramatic collapse moment to photograph. The timeline is measured in decades. Slow-moving stories consistently lose out to fast-moving ones in a news cycle built around immediate visual impact. As for any idea of deliberately engineered melting, the heat responsible for what is happening to Thwaites comes from oceans, absorbing roughly 90% of the excess energy trapped across more than 70% of the planet's surface. That is a force many orders of magnitude larger than anything any machine could realistically aim at a single glacier in Antarctica. The cause is diffuse, widespread ocean warming. The mechanism is physics that has been understood and measured for decades. What you should be watching for going forward is a specific announcement. The moment scientists confirm that the Thwaites eastern ice shelf has fully separated from the main glacier. Researchers genuinely believe this could happen at almost any point in the near future, quite possibly within the next year or two based on current fracture progression. When that moment arrives, it will not raise ocean levels by a single measurable millimeter on that particular day, but it will mark the moment the last natural break came off, one of the most closely watched and most consequential glaciers on Earth. The cork will have come out of the bottle. What follows afterward will unfold gradually over years and decades, but the direction of that unfolding will have been set. Multiple separate lines of scientific evidence, each built independently and using different methods, all converge on the same picture. The new bedrock map reveals the hidden terrain that allows warm ocean water to intrude so far inland. The fracture studies document the shelf's slow 2-decade slide towards structural failure. The global sea level record confirms that melting land ice has become the fastest growing driver of rising oceans. And the newest ice sheet models demonstrate that the tools proving most accurate against real-world observations are also producing the most serious forecasts. No single study tells the whole story. Together, they form a picture that keeps getting clearer, and unfortunately, as that picture sharpens, it keeps looking more serious rather than less. Antarctica can feel impossibly distant from wherever you happen to be reading or watching this, but the ocean connecting that continent to your coastline is not distant at all. That is exactly why a crack spreading through a slab of ice at the bottom of the world deserves serious attention right now, not in 50 years. The wall of ice the size of Florida is still standing. The single point holding part of it in place is still holding. But the measurements accumulated across 2 decades of careful watching, the fractures documented in peer-reviewed literature, the models calibrated against reality, and then projected forward all say the same thing with increasing confidence. The point is coming loose. The question is no longer if, the question is when.